Okay, I think we are live. I'm not sure if my ID is visible. Okay, I think it is. I think we are live. So, okay, so yeah, so welcome to this series. Here we will be developing distributed systems from scratch. And in the very first part of the series, we will be building Kafka. And I'm not saying that I know how to do this, so I have no idea. But like I have some basic idea of what goes into this. So we will be trying to emulate it and develop Kafka from scratch. So let's get started. Um, I think it's better to develop this in Go because that is something I'm familiar with. Mm, okay, I think I also initiated a project called Fafka, which is like some weird Kafka naming. Okay, I have not initialized the project, so I'll do that now. And okay, those who are new to the stream, so we are going to develop Kafka from scratch, and we will be doing that in Go. Along the way, I'll also explain different concepts that Kafka utilizes under the hood, and it won't be the very perfect implementation, but it will be something that can be used for like I'm not sure whether it can be used in production, but maybe with time we can develop it to such a level that it can be used. But uh, for now, I think it's more important to get started. Okay, so I'll call this project as Fafka, which is like a weird implementation of Kafka from scratch. Uh, so I'll just initialize this. Okay, we have the same problem. I like this is a common problem that I have been facing for some time. I don't think I think uh, okay, so we created this module. I'll increase the font size. I hope things are visible here, which I think they are. So my internet connection is a bit slow. I don't see very good quality, but I guess everyone else is seeing a better quality of stream. Okay, so now we have initialized this project. So um, I'll also create a main file. Okay, so our goal is to develop Kafka. I think it's better to have a README file initialized. So this will be a very simple but a good enough implementation. So we will try to keep adding the documentation on the go, but for now we can just run this program. I'll just print a hello world to see that everything is working fine. And it is working as expected. I'll also just check the stream to see my audio quality, and it is working as expected. I'll also just check the stream to see my audio quality. till now database. Yeah, so hmm. Yeah, so actually Kafka will be a combination of many things. I'm not sure whether the approach I'm taking is wrong or right. So that's why you can see that I have these many like these many AI agents on the side. So I will be taking their help. I'm not going to code everything from scratch and just like do raw coding. I'll be directing AI to write code for me, but the ideas will be mine. And along the way, hopefully, we will learn many things. Um, so this is a nice comment. So it's about I'm building Kafka, but it is almost like a combination of database, Redis, and web server, which is exactly correct. So we will have a we will have a set of producers. So first of all, I think we should understand how Kafka works and what it requires. So flip send backward. Okay, I think so. So this will be our Kafka implementation. So this is our server, and the comment is exactly right. This is a combination of database. Um, so I'll just write here. This is a combination of web server plus database and plus I think there was another term, database Redis web server. Okay, I so this is not exactly right. I'll instead of this I'll just write that is it's a combination of uh, brokers and kind of a database, but it is a simpler one, log based database. And also it is, I think for now, and a consensus protocol. So these are just some rough notes. Um, mhm. So like there are many things that we need to think about here. Let's start with the basics first. So what is Kafka? That is our very first question. So basically, whatever we use it for, it is mostly used as a queue. Whenever we need to produce messages at a very fast pace, we use Kafka for that. And like it's the backbone of many async workflows. So that's how we define it first. Um, so basically, it's a server, and I think it's better to call it server or like brokers. So it's like a set of brokers. So this is our Kafka backend, you can say, and basically we will have, for example, three brokers. So these are for high availability. So what are the things that we need here? So one is the brokers implementation. Brokers are simply the nodes we are sending our messages to, which will have their own partitions, um, like topics and partitions. So there are a few things that we need to understand. First of all, just don't think about this Kafka server at all. We can think about a topic. So basically, we have a topic. Let's call it as topic. Um, so every Kafka uh, server has a topic, and we simply publish the messages to this topic. And each topic can have certain number of partitions. So this is a topic, and we have, let's say, three partitions. So partitions is something that we can scale. So if like there are 10 partitions, we can have 10 consumers uh, pulling data from that topic. So 10 consumers will be attached to that topic. If we have like 11 consumers, then the 11th consumer will sit idle. So each consumer is assigned to one partition inside a topic. We cannot, and let's say that we have only one consumer and we have three partitions, then the consumer will just load balance between those partitions to pull the data out of that topic. So each topic has different partition, and this is called P1, let's say, and this is called P2, and this is P3. So a topic has multiple partitions, and we can think of it like uh, so we have like the server, the brokers, and they have certain number of topics. We will have a CLI tool to create the topics inside the brokers, and then we will have publishers which will publish to that topic, and then we will have consumers that will pull data from the topic. And if the number of partitions are like, let's say we have n number of partitions, we can have n consumers in a consumer group. So if I were to just complete this diagram, I hope that these things are visible. Okay, yeah. So if I were to complete this diagram, we have this Kafka server, which are the brokers, the server that will handle everything, that will handle all the connections, and then we have. So let's say that this will be consumer group 1. So the role of consumer group 1 is to connect to a particular topic. Uh, I think, okay. So we will come to that, come to the server or the broker's implementation later on, because that is not something we need to think about first. We need to think about like every server has a topic, consumers interact with the topic themselves, and other than that, uh, other than that, we have producers. So producers just produce to a particular topic. So we don't have any kind of any constraint on top of the producers. They can simply produce to a topic, and it will be automatically load balanced between different partitions. So what Kafka does is, like, if we remove one partition from the topic, the broker will rebalance that whole topic with the partitions as well as the consumers. So for example, if we have three consumers pulling data from three different topics, and we remove one, sorry, from three different partitions of a topic, and we remove one partition, then it will be rebalanced in such a way that um, so removing is fine. So one consumer out of the consumer group which was connected to that particular partition will sit idle. If not, if we add one extra partition, then the three consumers will be pulling the data from four different partitions. So we can think that maybe one consumer will pull data from two different partitions, and the rest will function as they were doing before. Okay, so these are some basic things, and this was not at all structured. I'm planning to write a good article on this. So based on the video that, like, I'm shooting right now, so that people can get a good understanding of this. But for now, what we can think is that we need a TCP protocol. So as in the comments, someone said that yeah, hi Vishal. So as in the comments, someone said that it is a combination of database, Redis, and web server. I wouldn't say that it's a web server. Uh, what we can think of it is a protocol in itself. So I would say that Kafka, so it's basically a TCP protocol. So it will be a server, a long running operation server, whatever you think of it. And it will be TCP protocol based. And we will have a client, we will have our own library that consumers or producers can import and then use that to send messages or consume messages from the Kafka topic. So what we need to do is, like, our server will have certain topics implemented. Our server will have functionalities like create a topic, okay, and then push data to a topic, and then pull data from a topic. So these three functionalities will be there for our Kafka server slash brokers. So our server will be a TCP protocol, and that's how we start thinking about it. So I'll just write some note here. So our server will be a TCP protocol implementation. And what are the APIs that I can think of? So one API would be create a topic. And okay, and there's a very important thing that I missed discussing here. So to make our Kafka highly available, we must have like multiple servers or multiple nodes. So what we can think of it as like a server will start up and it will connect to a different node. So for example, if there are two nodes, they will just broadcast themselves to each other so that they can connect with each other, and then and 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 like assign a leader. So two servers will connect to each other, assign a leader. We will push data to one server, which will be replicated to the other server also. So there's a lot of complex things going under the hood. We won't be implementing everything, but we will implement some of it to get the idea of how we implement this whole thing. So that is one thing, and that is also part of the implementation. But for now, we can think of it as a single server for now, and we'll just make sure that we'll just assume that this is a single server, it's highly available, and then we can implement the consensus protocol on top at a later point of time. So let's say that API, assuming that this is a single server for now. So we can create a topic, we can push message to a topic, create a topic with a single partition. So again, we will have multiple partitions at a later point of time, but for now we can think that our topic will have a single partition only. And then we can push messages to a topic and it will just go to that single partition and then consume message from our topic. And then we can consume messages from our topic. Okay. Cool. So now what I'm going to do is I'm going to feed this to Claude. I'm trying to make a simple Kafka protocol. Just help me create a simple TCP listener. Which can accept like certain kind of messages, like create topic name, and then push message to the topic, and I think we can call it as produce and consume. So we will again consume message from our topic. This will also update the offset. Okay, so while it is doing its magic, So one thing that we need to think about is that when consumers read from a topic, it also updates the offset. So let's say that consumers like certain messages are going inside a topic, and uh, let's say that the messages are M1, M2, M3 in that order. So the producer will produce these messages. Then the consumer will then consume these messages as again in the same order M1, M2, and M3. It is kind of a queue. So producer produces the messages, then consumer consumes the same message. Let's say that it consumes one message at a time. Then after that, it updates the offset. So the consumer then updates the offset, or the broker itself updates the offset that this consumer has read the message, and then I think it commits that okay, I've read the message. Um, then obviously the Kafka broker will update its offset for that consumer inside that consumer group. So we know that like when it reads the next message, it will read it from that particular offset. So basically what we like the database here is simply uh, a log based database, a log based file. So basically it's just a file, and this is what I was thinking. Basically we will have a file, we will just keep appending to the file, and then we will keep reading from that file for that particular consumer. So the consumer will read from the file, and it will also have that offset, so that maybe it can just seek like form a seek operation on that file. Again, I'm not sure how it's done, so maybe I can go to Gemini and ask that can we seek a file with a given offset, and also we need to understand that what is the complexity of this operation, because we need our reads to be as fast as possible. So in most programming languages, seeking to a specific offset in a file is a standard operation. It allows you to move the file pointer to any byte position within the file without reading the preceding data. Move to 1024th byte from start. Okay. And this is for Linux sequential. So what is the complexity of this operation? The time complexity of this operation is O1. And this is pretty cool because this is what we want to do. We are basically writing to a file, and we are writing very quickly to that file. Obviously, once that file gets filled up, we can then move on to write to the next file. So maybe like this is the data that we want. We want that which file are we reading from, and also the offset in that file. So basically, if we have a fixed file size, let's say that our file size is 100 bytes, and we are reading uh, like let's say the 503th byte, then dividing it by 100, we get 5. We get 5, so we know that like it is the fifth file that we need to read from. And then we also do the modulo operation. So 503 mod 100 gives us 3. So we know that the third byte is the one that we need to read from that file. Um, so yes, I think that will be a very quick operation. We don't need to maintain too many pointers. Like for this consumer, we need this file number as well as this particular offset inside that file, I think. So this is our implementation. I'll just copy paste this. Okay, and it has also given us a way to produce and consume the messages. Okay, and these are the features that we have. So the TCP server is on port 9092. We have the create topic command, which creates a particular topic. Then we have the produce message, which is stored in memory. Okay, so for now, I think in memory is fine, but later we will move this to file with a val kind of a thing. So val is like write ahead log, and again that is also something that we should implement. uh, some features that I'm thinking, um, a server, producer library, consumer library, which can be used by consumer clients. Okay, and val for durability. So whenever we write messages to Kafka, we obviously need to write it in a file, but so that is an operation that can be done later on. Maybe we can write to in memory and we can have like a write ahead log also implemented. But since we are writing to a file, I'm not sure whether we would want that or not. We are writing to a file. Do we need this? I'm not sure. So these are some things. Okay. I'll also ask Gemini to like create a diagram for this basic Kafka implementation and enrich the notes. So I think it's better to create a diagram and then also make these notes better, so that anyone looking into this at a later point of time, even if I'm looking into it at a later point of time, I can think that okay, this was my chain of thought and this is the point from where I can continue. Um, okay, blah 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 blah. Answer: no, you don't need a separate val in this architecture. The data log is the val. So since we are writing to the file, we don't need to implement a separate val thing. So why do we need a val here? Because I think it's better like in some case of like in some other data structure like Postgres. um, Postgres is not a log-based data structure. We need to have proper indexes, and it is a tree-based data structure. So in that case, when we need durability, we write to the val and then write to the actual table later on. So even if the system goes down, we can say that at least we have that data in the val itself, which we can then move to the actual table. So in Kafka-like system, the actual data table is just an append-only data structure, which it is telling us. So we can just flush it to the disk and we achieve durability. So I don't think we need that. Uh, yeah, and this is what it's saying. So for example, when we create a topic, it can create a log as well as the index, crucial for own reads, explained below, the actual message data. Okay, so inside this we have the messages and then we have the index related information may be stored here. Producers always append to the end of log file. The offset is just a monotonic integer identifying the message order. Index file. If a consumer asks for offset 5000, how does the server find it in a 10 GB log file? Scanning from the start is O1. We need the O1 seek we discussed previously, the index file pairs logical offset and physical byte position. Okay, example, we don't need to index every message. We index every say 4 KB of data written, offset 0 points to 0 byte, offset 150 points to byte 4096. Okay, cool. Okay, so it is not as simple, uh, because our messages can be variable. So what I said was that, like for example, let's say our message is only 501 bytes, we can divide it by 100, um, and then we can do a modulo operation and then read that one like the first byte in the fifth file. But we don't want to do that because our messages can be of variable length. So we need to index that. Let's say this byte is for this offset, so we can have like mapping every 4 KB, which it is saying. And first we need to read the dot index file to get the specific mapping, and then we can do a read from that point. So basically, so 4 KB is 4096 bytes. So even in the worst case, our performance would be O of 4096, because even in the worst case, we are just reading, like seeking to go to the 4096th byte. So I think this is a good thing. And again, when we design this, we cannot think of this index to be very large. Like we cannot keep on indexing at very large points of time, because then our seek operation takes longer, and we cannot also index very frequently, because then the number of writes just goes up. So basically, the size goes up or the processing time goes up, and this is a classic uh, like dilemma we have. We need to choose a value such that both of them remain balanced. We cannot like focus on increasing the dot index file size and decreasing the speed, or we cannot just keep on like have a high read operation, like have a low duration, low latency read operation, but we have like large index files, so we don't even want that. Okay, so this is the thing that it's doing. There are many things that go in here. For example, this fsync thing, I'm not sure what is this operation, but I've like read about it many times. I think like whatever we write to in memory, when we call fsync, it is written to the disk, but I'm not sure. I'll have to look into this. So it has given us a bunch of things to think about, and cool. I think so. I'll just copy paste this thing for now. So basically, it is storing the messages in memory, and then we have this offset. So server is just a list of all the topics, and then we have a mutex, which is like we are locking the server so that uh, obviously we don't need to override the same thing. So we are locking the server, and this is thread safe. Um, and now comes the main part. So we have this handle connection, which starts the server, I think. Okay, so we have this new server function which has the server object, and then we start a TCP listener on port 9092, and we simply accept the connections and handle the connections. So we can have like multiple producers interacting with our backend here, with our server here, and since our server is thread safe, we don't need to worry about whether our whether our data will be overwritten or not. So yeah, that is one thing. Now coming to the handle connection function, so basically it's just scanning everything and then writing the response back. Okay, so it's just returning the same response, I guess. And then we have this handle command function. So for now we have like three commands: create, produce, and consume. So create will just create a topic, and we have like a set of topics created in memory, and then we have this produce function which will just append to that topic and increment the offset, I guess. And then we have the consume function which will consume from that topic. Okay, so consume is, so like consume takes in two arguments, the consume itself as well as the topic name. So first we are locking the topic, and then we are reading from the topic, and obviously we are incrementing the offset because we don't want to read the same message again. So whenever we are reading from a topic, we increment the offset. And coming to the produce function, we have the topic name as well as the message. So we are appending the message, which can be a variable byte length, to that particular topic. And then we have this message count. that is the number of messages on that particular topic. So this is a pretty easy to understand implementation and pretty simple. I guess we can just start our server. So our server has started and these are the commands. Uh, then we can just do this and see localhost to how do I create a new terminal? Okay, split terminal, create terminal, move. Okay, this is our terminal nc localhost 9092 since it's on that port. So we have connected to the server. If I just go here, it shows that a client has connected to our server, to our backend, and then we can create a topic called orders. Let's say that we just do something, some random gibberish. So it throws the error that the command is unknown because we have because like that is the default message that we are returning, that it's an unknown command. We are only supporting 3 commands for now. So let's create a topic, create orders. So the topic is created, orders. Oh, okay. Okay, so it has created the topic. Oh my god, this is confusing. Okay. Okay, so now we have our server running and the first topic was orders, which is now created. What are we going to do here? Okay, so let's also connect this other client, localhost 9092. So now our server should show that like 2 clients have connected to it. Now what are we going to do here? So in the first client that was connected, we just created a topic, and then let's say that we produce this message, hello world, or hello from Kafka. So that is created on orders topic, and then we have like consume command. Now we have again now we have read that message from the topic, and then consume orders. If we run this command again, then okay, that was the wrong command, consume orders. So no messages available because we have already consumed whatever was available on that topic. And since we have this single consumer, so basically I think whatever consumer we create, I think even if we create a third consumer and see local host 9092, we will separate this out into a different library in itself. But for now, I'll just have this on like on the terminal itself. So consume orders. So there are no messages available for us. There are no messages available. Okay, and you can see that we have like 3 different consumers connected, 3 different clients connected to our server, and the first client is just producing messages and the rest 2 clients are reading messages. And similarly we can have like another client which will just produce message, and the other 2 will consume message. Okay, so let's produce another message, produce on the topic orders, and ABCD, and then produce orders 1 2 3 4. So consume orders, consume orders, consume orders, consume orders. So you can see that we have again consumed both the messages, and now, so this is working as expected. But obviously, what is wrong with this? So first of all, we are holding everything in memory, which is wrong. What we want is we want this to be durable. So we want to write everything in a file, and now our like multiple consumers will be reading from the same file. So we need to also store that offset. We need to write that offset in the index file, or not in the index file, but we need to have like some setting where we also store that which consumer. um, so obviously, like if you can see, then like the two clients here are acting as consumers. So this is part of a single consumer group. So what happens is that when we are reading from a partition, and inside a consumer group we have like two different consumers. So consumer group can have like many number of consumers, and each of them will be reading data from that topic. And clearly, they will, like if one consumer reads data from a topic, then that data is not available to be read from other consumers. So that consumer reads the data from that topic, it updates the offset, the other consumer will read from that particular offset. It won't just uh, it won't just read the same data twice. For that, we need to have like two different consumer groups. So two different consumer groups can subscribe to the same topic. So this is consumer group 1. I'll just keep these things here, and this is consumer group 2. So like these two consumer groups will be reading from the same topic, and the offsets would be different from each consumer group. So that is one thing. And then again, and this is for a single partition. If we have like different number of partitions, then we need to have the offset among different partitions. And then we also need this thing where, and again, this is on a single broker, on a server which has a single broker. Now if we have multiple brokers, this data needs to be replicated across brokers, which is a thing in itself. So when we think Kafka and we just have this underlying data structure where we just push messages to a particular topic and just consume messages to a topic, if it is like not scalable, we just increase the number of partition. Kafka handles the rebalancing and like all the syncing and stuff, and we just don't worry about it. So that's the abstraction that we are working on. So under the hood, if you just start implementing this, if you just implement like start with a single topic, a single partition, a single broker, a single consumer, then it is easy to think about. But when you have like multiple nodes for high availability, and when you write this data to disk and store different metadata for that consumer group, then things like start becoming very difficult. And now this is one of the concepts that I would like to talk about. So the concept of this consumer lag. So when producer like produces topic at a very fast pace, so this is something that I just like recently faced in production. So when consumer produces to a topic at a very like fast rate and like fast writes, and the read is not that fast. For example, we might have like less consumers, or even in most of the cases the bottleneck is the data that we are writing to. So it's not that just the consumer consumes messages. So it fetches the message, it does some operation, and then it commits the offset. So that's how a consumer works. So like it's a three-step process. And if that operation that I was talking about, like let's say that we are writing to a database, if that is slow, then committing the offset is slow, and that consumer is taking time to consume that data. And this is why we like see this consumer lag. So this is just a like a divergence that I went through. That is something that we will again discuss in the future, but for now I was just trying to explain that things can get out of hand if we just think about a single topic, a single partition, a single consumer, a single broker. Things are easy. But when we just add the number of brokers, add the number of partitions in a topic, and we have like multiple topics, and then we have like multiple consumers in a consumer group, just things are not that easy. And then we are also talking about the consensus here. So I think Kafka moved from, like, then we had Zookeeper. So Zookeeper used to store all this metadata, but that was a dependency. I think that has been removed recently. So Kafka has moved to its own consensus called Kraft, I guess. So it is taking care of everything by itself. The whole broker, like the whole server, which has like a set of brokers, is handling the metadata itself. Uh, so that is another thing. I think for today, hmm, I think we have discussed a lot today, and I'll just, um, I think we can, so I'll just read on this more, and then maybe like next time I'll just move to the second part of this implementation. But for now, I guess this is enough. So basically, just to summarize, what we did is we used Claude, first of all. So we used Claude, and then we created this basic implementation where we have like 3 commands, and we are assuming that we have a single broker, a topic with a single partition. So in our implementation, we have a single broker with a topic, obviously like a single broker, so it's a single server that is implemented, and that is fine for now. And then we have a topic with a single partition. We are just writing to that topic, and whenever we are consuming from the topic, we like we are assuming that every consumer is part of a single consumer group, so we are just consuming messages from the same topic. So that is one thing. And yeah, so this is a very basic implementation where we just start a DCP listener, and everything starts with this. We start a DCP listener, we keep on accepting the connection. For every connection, we handle the connection using a Go routine. So every connection that we accept is handled in a separate Go routine, and that is why we are using lock on a topic on our server, so that we we don't have any uh, like data race or anything. So that's why we are using log for every topic and on our server. So a server is just a map of various topics. When we are creating a topic, we are adding the topic to a server, and then we are producing and consuming from that topic. So handle connection just handles the command, and the command can be of the format create a topic or produce some message to a topic or consume a message from the topic. And the important part here is that everything is in memory. So we are not reading anything from a file. That is something that we will do in the next video, where we are, instead of like reading and writing messages to the memory, we will use file with that fsync operation or command. I'll also look into it and see that how we can make this implementation better. um, yeah, I think this is all well for now. uh, yeah, so thanks for joining the stream, and I'll see you in the next one, where we will uh, write to the file instead of writing everything in memory, because obviously this is not the best of implementations, and this is not how production Kafka looks like, obviously. And once we're done with that, then we will think of adding like multiple consumer groups, and also adding the metadata to our file. And for now, we will just do everything on a single server, and then at a later point of time, we will have multiple servers connect to our server. So basically, like multiple brokers connecting to our like current broker server, and then they will have their own consensus mechanism. Maybe we will use Raft or something, but that is something that uh, will come across at a later point of time. For now, I'll just end this with the note that in the next video we will be implementing a file system. So we will be writing every data to the file. For now, we are just writing to in memory, which is not the correct implementation. So yeah, see you in the next one, and I'll also like create a tweet with the diagram and everything. So yeah, thank you.